went through a bunch of this on Tuesday. We talked about just a quick review of linear acceleration, and then we talked about how the kinds of acceleration we're thinking about for rotating objects for right now are these two, which are linked to each other. Angular acceleration, which we use the term alpha for, and tangential acceleration, our variable is a with a little t, and these are linked to each other by the distance that the rotating object is from the center of rotation. Specifically, alpha is equal to tangential acceleration divided by that distance. The units matter for this stuff. You don't have to use the units that we do. It's just that the equations won't work exactly right if you don't. So we've got to make sure that our angular measurements are in radians, or radians per second, or radians per second squared. Our linear measurements should be in meters, or meters per second, or meters per second squared. And our times should be in seconds. And if that's the case, then this equation will always work for an object. Even, its speed could be changing, but at any one time, if you know an object's tangential acceleration and how far away it is from the center of rotation, a division can give you the angular acceleration. Of course, you can find tangential acceleration by multiplying the angular acceleration by r. That only works if you're using radians. These two kinds of acceleration, I said, centripetal acceleration you don't need to worry about now. We will be talking about it later. Overall linear acceleration is something you should know if you're in AP physics, but it isn't. We're not going to do anything with it in this class. And then I went through our two quantities that factor together to determine angular acceleration. And those two quantities are torque, specifically the overall torque acting on an object, and you'll see in a second, like it's possible to have, just like we can have two linear forces acting on an object, we can have two rotational torques acting on an object, or more. They can be different strengths, they can be in different directions, and the combination of those two things will in part determine an object's rotational angular acceleration. And then the other piece was this moment of inertia. And moment of inertia it's a really complicated term that is not meaningful to most people. Most of us have some idea of torque because it's a car thing, if nothing else. So many of you have heard that in the context of cars, and we know it has something to do with like towing and stuff like that. But when I explain torque as force with leverage, that sort of makes sense to people. The idea that if you want to rotate something, if you've got a bolt that's stuck, if you use more force, you might be able to get it unstuck, but you could also use more leverage, and then you don't need to use as much force. And those two concepts are pretty familiar to us because we use them a lot. We use the idea of not necessarily the word, but we apply leverage all the time. So leverage is the thing that we get. Moment of inertia is weird because none of this means anything to most of us. Inertia doesn't mean a ton. Certainly the idea of a moment of something doesn't mean anything. We use the term moment to talk about time, and this has nothing to do with time. I would advise you to, in your get fluent at replacing this term moment of inertia with angular mass, because that will make a little bit more sense. And we'll look at a couple different ways to think about it today, but in general, the idea is that things are more difficult to change the rotation of if they either have more mass or if they have mass that is farther from the center of rotation. And you'll be playing around with some things, you'll have the opportunity to play around with some things where you can see this in action. But most importantly, you can visualize it. Imagine that you were driving your car and it had a steering wheel that was, let's say it's kind of big, like an oversized steering wheel, like a semi-truck or something, so it's this big. And imagine that you're trying to turn that steering wheel. Now imagine that somebody takes a big, heavy weight, like something really heavy, like 20 or 30 pounds, and they put it right in the center of that steering wheel. Well, if you put a big weight right in the center of that big steering wheel, it's not that hard to turn the wheel. You're turning the weight, but it's just, you probably wouldn't even notice the difference that much, and you can sort of imagine it. Now imagine taking that same weight and putting it on the outside of the steering wheel. So now when you turn the wheel, you have to make that weight move a whole bunch to get it to move along with the wheel. And you can imagine you would feel that a lot more. And it's true, that's exactly how angular mass or moment of inertia works. Getting familiar with that idea is more a question of practicing. Like actually moving things around, getting things to move in circular paths with different moments of inertia. You'll see, when you increase the mass of something, it's harder to change its rotation. If you take an object's mass and you move that mass farther away from the center of rotation, the same thing happens. And we have things that you'll be able to play around with where you can see that. We have a rotating platform and you can put weights on that platform in various spots, and you'll be able to see, oh wow, when I put the weight in the middle, it doesn't really change how hard it is to speed it up or slow it down, but if I put the weight out at the edge, I can feel it. You can do that with the rotating platform that we have. We'll do that with people. You will be able to have a person holding weights, and that person can hold weights closer or farther away from the center of rotation, and you will feel the difference in how hard it is to get them to change their motion. So we'll look at that in a little bit more detail with some hands-on stuff today. But what I want to do is put all this stuff together and look at Newton's second law. So when we were dealing with linear motion, we had a version of Newton's second law that we applied a bunch, and that was that the sum of the forces on an object, the net force on an object, will equal its mass times its acceleration. And it turns out that the angular version of this is exactly the same, but it just uses the equivalent angular variables. So Newton's second law for rotating objects says the overall torque, if you have one torque on an object, then that is the overall torque. If there's more than one, you add them all up. If they're in different directions, it's the difference between them that matters. If you have one torque that's counterclockwise and one torque that's clockwise, the sum of those torques will be the difference between them, right, mathematically. The sum of torques on an object, the overall torque, will equal its moment of inertia, which is angular mass, times alpha, which is angular acceleration. In other words, for any given object, you will get more angular acceleration. Its angular velocity will change faster if there's a greater overall torque, or if there's a smaller moment of inertia. With linear motion, we can't change moment of inertia. We can't change mass easily while an object is moving. If I'm pushing something around, its mass is fixed. Moment of inertia is kind of cool though, because we can change that relatively easily by changing the distribution of mass. That can happen with mechanical systems, but it's easier, really easy with people. Because if I'm rotating, if I'm spinning around, if, for example, I'm carrying two big heavy weights in my hands, I can easily move those closer or farther from the center of rotation, thus changing my moment of inertia, which is a weird thing to think about, but it works. Yeah?
Would that kind of also apply to things like buckets of water, like if you were rotating like something sort of like...
Yeah. Yeah, so if you have a mechanical system, there is a tendency of objects that are free or partially free to move toward the outside of rotation. So if you've ever done your own laundry, You've probably noticed when you put the clothes in the washer, they're sort of evenly distributed, but after it's gone through the spin cycle, all those clothes are on the outside. So that is a change in the location of the mass inside the washing machine. A centrifuge does the same thing. Centrifuge spins things around in a circle like test tubes. And that will result in mass being distributed farther away from the center of rotation. We have, and we can pretty easily see systems where there's objects on springs that are spinning in circles, and the faster those objects spin, the farther away from the center of rotation they'll be. They tend to move away from the center of rotation on the spring. So we can change moment of inertia with mechanical systems as well as biological systems. So just remember that angular acceleration here is rotation. The units are radians per second squared. So we are thinking about a change in an object's rate of spinning. And angular acceleration is how quickly that happens. So as I just said, overall torque, the more there is, the greater angular acceleration will be. And the greater moment of inertia is, the less angular acceleration there will be. And we have, for both of these quantities, we have two things to consider. For torque, we need to know how much force is being applied and how far is that force from the center of rotation, because both increases in either of those will result in an increase in torque. For moment of inertia, we need to know how much mass there is and how far away that mass is from the center of rotation. Increasing either of those will increase the resistance to changes in rotational motion. When we talk about moment of inertia, many of you are going to think, okay, well, we can calculate it. And many times that's true. If we have uniform objects or very nearly uniform objects like this, then we can just say, oh, well, basically what's going on here is this is really similar to an object that has a infinitely thin radius where all the mass is located at the exact same distance from the center of rotation. We can essentially pretend that this is an infinitely thin hoop spinning around. And in that case, we know what the moment of inertia is going to be. We can calculate it. It's just going to be however much mass there is times the radius squared. And that is determined, we know that mathematically, but we figured it out experimentally as well. Effectively, what we're looking at in moment of inertia is the overall sum of the mass of each particle in a thing times the distance from its center of rotation squared. So there are some things that are uniform, and we kind of know how the mass is distributed, and we can just plug our mass and some aspect of the dimensions of the object into a formula. And that's easy for things where it's like a hoop or what we call a point mass, which is just something that is relatively small. If I wanted to know the moment of inertia for this point mass, super easy. I just need to know its mass, and I need to know how far away it is from the center of rotation. M times r squared will be the moment of inertia for this object. If I take this hoop and I spin it around its center like this, the moment of inertia will be the mass of this hoop times the distance from the outside of the hoop to the center of rotation squared. Other things like cylinders, solid blocks, discs, something like this is basically a disc. It turns out the moment of inertia of this is going to be about 1/2 mr squared. So put this on a balance, find the mass, measure the distance to the outside of the plate. 1/2 mr squared is going to be the moment of inertia of this disc. I said about. And the reason that I said about is because this isn't actually uniform. If you look at this object, you'll see there's a little bit of extra material right here. It's not quite 1/2 mr squared because there's a little bit of bulge here. If this were perfectly symmetrical, perfectly uniform, flat disk, we'd be good. Then there's other things that get more tricky. So if we were to look, for example, at something like this, now our mr squared, 1/2 mr squared, like, it's a little bit more complicated because there is a hoop part to this, the outside of the tire, but there's also like a significant amount of plastic here. And you might be like, well, plastic is light, but actually, so is the outside part of the tire. There's not much weight here, so this is kind of light and this is kind of light. And then there's also this whole hub part, and a bunch of that is spinning. And then there's the handle, and I can see there's some metal in there, that's not spinning at all. I don't know what the moment of inertia of this tire is. I could weigh it, and I could put it into an equation, but I don't know if that's really gonna give me the moment of inertia, because not all of the mass is spinning, and I don't know exactly how that mass is distributed. Maybe it's 1/2 mr squared, maybe it's closer to mr squared, maybe it's 1/3, 1/4 mr squared. I don't know. So when we have a more complex object, we have to determine the moment of inertia experimentally. There is no equation that we can just plug it into, plug mass and dimensions into to get the information we want. You're going to be using these. These have a relatively low moment of inertia. If you weigh the mass and you measure the dimensions of this concentric pulley, you will not find its moment of inertia. Why? Well, because it's not uniform. It's actually pretty close to uniform, but it's not entirely uniform, but mainly because the majority of the mass of this thing is in the metal handle that doesn't spin at all. So measuring the mass of this thing and trying to figure out something about its dimensions will tell you nothing. What's going to happen is about half of you are going to try to figure out the moment of inertia of this, or of that bicycle wheel, or of some other object by measuring its mass and plugging it into some formula that doesn't apply to that object. We have equations for moment of inertia that we can use for uniform, regular shapes. As soon as we have an object that is not uniform and or regularly shaped, we cannot use any of these equations. So that, in particular, that's going to apply to objects where, for example, a significant portion of their mass isn't even rotating. This rotating platform is another example, something where you can measure its mass if you want, feel free, and you can measure something about its size, but that will tell you nothing about the moment of inertia because most of this thing isn't spinning at all. So you're not going to find the moment of inertia for this object by making a measurement of mass and size. Here's another example. You're probably wondering, why do I keep all these things up here? Do you know why? You can guess. What's that?
For this purpose, precisely.
Well, no, yes, that's why I have them to begin with, but the reason that I keep them up there is because anything I leave out gets broken. The other day, Mr. Viskin and I spent like 10 minutes cleaning up broken glass because we made the mistake of leaving light bulbs on the counter. And I don't know who breaks this stuff. It's hard for me to imagine it's you, but then it's hard for me to imagine it's anybody. The idea that somebody could break a piece of glass and then just walk away is mind-boggling to me, but it might have been one of you, so. So if it was you, congratulations, you boggled my mind. But I always tend to blame people who aren't here, like, no matter who's in this room right now, I'm like, well, it couldn't have been you, but, you know, somebody did. Maybe it was me, I'm not a I did this accidentally, but I don't even notice. So here's an example of something. If I want to know the moment of inertia of this, seems like this is pretty uniform. I mean, it looks like this, right? And if I were to rotate it about its central axis right here, that seems like something I should be able to, like, think I could probably work with that, right? Just measure the mass, measure the length. But here's the problem. Let's see, Allison, will you stand up? Take these, and I want you to just wiggle them from the center, like that. You feel the difference?
Yeah.
They have about the same mass, though. Here, you try it. They have about the same mass, but the mass is, yeah, isn't that the weirdest thing? The mass is distributed differently. So these, I want you to play with at some point today, because what you'll notice is, if you lift them up, they feel like they're the same. If you move them side to side, they feel like they're the same. But as soon as you start to rotate them, you see, oh, they're not the same. The distribution of mass is different. In the blue tube, the mass is farther away from the center of rotation. In the red tube, the mass is located right here. By the way, the red tube is breaking, which is ironic since it's just been up there. So what that means is, you can't just measure the mass and the size of something to find its moment of inertia. And I'm gonna stop emphasizing that now, because those of you who get it, get it. Those of you who don't get it need practical experience. It's so easy to fall into that trap. Yeah. So easy to fall into that trap, but you have to train yourself to not fall into that trap. And then let's see. Okay, so yeah, get that out of there, Dan. Sorry. Okay, so I'm going to just go through a couple of things real quick so that you can kind of see the kinds of things that we need to think about. So, given our Newton's second law equation for rotating objects, if we keep everything else the same, but we apply a larger overall force, then we should see larger angular acceleration, okay? Because increasing force will increase torque, which will increase overall acceleration. If we push with a force, and then we push with that same force, but we move it closer to the center of rotation, we should see a smaller angular acceleration because we have less leverage. Torque is force times leverage. So the overall torque will decrease as we move our force toward the center of rotation. If we have a tube that's spinning around and we add mass to it, we should see less angular acceleration, all things being equal, because it's going to resist changes to its rotational motion more. If we take mass and redistribute it so that it's closer to the center of rotation, we should see more angular acceleration. You will see more angular acceleration for any given torque on the red tube than you will on the blue tube, because the mass is closer to the center of rotation. They feel the same when you do this, because they have the same mass, but I can wiggle this one back and forth a lot faster because I can change its rotational motion a lot more. That mass is closer to the center of rotation. All right, and then if we wanted to find the moment of inertia for an empty tube, and this is a little bit misleading because where the tube is being rotated matters, but if you wanted to find the moment of inertia of an empty tube, you can do something like, I'm not going to do it right now. You can do a Google search. What is the equation to find the moment of inertia for a hollow cylinder? And then you have to figure out where it's rotating, and it will give you an equation. And that equation, you can take it to the bank if you have a uniform cylinder, known mass, known size, rotating about its center the way that we were rotating our hollow tubes the other day. This is a little bit trickier because if we have a hollow tube, but we put two of our metal bars far from the center of rotation, we can just add the moments of inertia together. So whatever this gives us will be the moment of inertia of the tube itself. The moment of inertia of a single point mass, like a bar, that is 30 centimeters from the center of rotation, is going to be mr squared for each of those masses. and we can just add those together. So the overall moment of inertia of a hollow tube with 2 point masses on it would be whatever the moment of inertia of the empty tube is, plus the moment of inertia of one of those masses, plus the moment of inertia of another one of those masses. So we could find the moment of inertia of this object. What we would probably do for something like this is assume that the moment of inertia of the plastic bar itself is basically 0, because it has so little mass compared to the weights. The moment of inertia of this thing is going to be effectively mr squared for this plus mr squared for this. We can ignore the plastic tube because it has so little mass. We can find the moment of inertia for this the same way. Just ignore the plastic tube. We have one mass here, one mass here. It's going to be mr squared plus mr squared. I think their masses are almost certainly the exact same. I haven't broken it open to make sure though. So we actually can calculate it for these tubes, but as you start to look at more complex objects, the rotating platform, our concentric pulleys, or the bicycle wheel, those become far more difficult to think about. All right, so I'm gonna go through just a few examples here real quick, and I'm gonna have you start thinking about equations and work in this same way. What I want to do first is just remind you that we have kind of 2 realms. That isn't the pen. Sure. Come on, you can do this, I swear. No, please. Please work. I need you to work. You need to be able to write. Oh, this is just no good. This is so bad right now. All of this is bad. Ah! Curses. Like, it's not just this. Oh my god, this whole computer is just like dying a slow death in front of us. Alright, well, that sucks. Here is, gosh, this is frustrating. Okay, so here's what we have. We have a whole set of equations that work for objects that are moving in a linear fashion. We have our kinematic equations, like object's final position will equal initial position plus initial velocity times time plus 1/2 times the acceleration times time squared. We have the sum of the forces on an object will equal its mass times acceleration. We've got some like equations that we can use to think about the motion of an object that's moving linearly. We also have a bunch of equations that work for angular motion. And some of those equations kind of are analogous, like if we know an object's initial angular position, its initial angular velocity, and its angular acceleration, we can figure out what its final angular position is going to be. This is the same kinematic equation, just in rotation language. We have sum of torque on an object will equal moment of inertia times alpha. And then we have some other equations too, like we may have some equations potentially if we know enough about an object's composition. It may be that like the moment of inertia for a point mass is equal to mr squared, and I wouldn't expect you to have that memorized, but you could look it up. If you know you have a gewgaw spinning like this is effectively a single object that's just rotating in space. The string has barely any mass at all. We can just pretend like it's an infinitely small mass rotating at whatever distance this is, and use an equation to find its moment of inertia. And then we have all these connections. We have these ways of moving back and forth between some linear quantity and some angular quantity. So for example, if we know an object's linear equivalent distance, if we know how far something travels along its curved path, and we know how far it is from the center of rotation, we can find its angular position or displacement in radians. And if we know an object's angular acceleration, we can find its tangential acceleration if we know how far it is from the center of rotation. And taking all these equations, knowing how and when to apply them, allows us to solve a whole bunch of relatively complicated problems that I'm probably not going to be able to write because I don't seem to be able to like select pens with this thing. Oh my word. It's almost like I'm almost embarrassed for the people who like put this stuff together because it's not shouldn't be that hard to like have a menu that doesn't disappear when you click on it, but that's all right. So if we were to think about something like this, we have a bunch of numbers: 18 newtons, 2/3 along a door, 0.99 meters wide. There's all these things that we need to think about. But in general, with all the work we've done and all the work we're going to do, it makes the most sense to start with variables and just think in terms of variables. So if we want to know how much torque is exerted on something, well, torque shows up in a couple of places. Torque shows up in this equation. Sum of the torques is equal to I times alpha. So if I want to know torque, if I can figure out moment of inertia and angular acceleration, I can do it that way, but I don't have a ton of information here. So it doesn't seem like this is going to be super helpful. But I also know that torque is equal to the amount of force applied to an object times the distance away from the center of rotation that force is exerted. So that, here, I think we've got something to work with. And in fact, the easiest way to think about this is to just leave it in terms of variables. How much force is it? It looks like 18 newtons. How far away is it from the center of rotation? Well, it's going to be 2/3 times 0.99, 0.66. We can do that calculation, but we don't even need to, because now we've got a general equation. We know force, we know where that force is located. We're done. We don't need to actually do any more math here. What if the force isn't perpendicular? Those of you in regular physics aren't going to have to worry about this. Those of you in AP physics are going to have to think about this. So if the force is at a 60-degree angle to the door, if this is my angle right here, only the component of that force that's perpendicular will matter, and that's going to be the amount of force times the sine of that angle. So in this case, it's this. However much force is being applied times the sine of the angle times how far away that force is being applied to the center of rotation. And this, so as the angle approaches 90 degrees, sine approaches 1, and you get all of that force contributing to torque. As the angle drops to 0 degrees, if you push on a door in the direction of the door, not perpendicular to it, you won't get it to rotate at all. I can't open this door by pushing this way on the door. I could push as hard as I want and it will not swing open because none of the force that I'm applying is going to torque. There's no rotational force being applied here at all because I'm not pushing perpendicular to the hinges. So we've got another sort of general equation that we can use, and those of you in AP physics will need this. If you're not, you'll never need to worry about this again.
Why is the arrow pointing direction facing towards the object?
It doesn't, because it doesn't matter. I'm imagining, because it doesn't specify. You'll get the same number either way though. You could be pulling, or you could be pushing. You could be pushing like this, or pulling like this. Either way, the calculation of the force is always going to be the same. It's always going to be however big that force is times the sine of 60 degrees. So I just picked one out of the 4 possibilities to draw. All right, here's another example. Calculate the moment of inertia this is a regular object, the axis is through the center, we have an equation we can use, so we could do that calculation relatively quickly. Here's one where we have a bicycle wheel. What's a bicycle wheel? Well, it's basically a hoop, and the moment of inertia for a hoop is mr squared. A hoop and a point mass are effectively the same thing as far as rotation is concerned. And so we could calculate this as well. These are really easy calculations, and then all of a sudden you have something like this. A 1.84 meter diameter sphere rotates around its axis. It's experiencing a torque, and we can assume in this case that this is the overall or net torque of 12.3 Newton meters, which are the units of torque, force times distance. If it starts at rest and rotates 180 revolutions in 15 seconds, what is the mass of the sphere? So let's see if you can do this. That's like, you've got whatever resources you want. You can work with other people. You can look at the equations that we've got, but let's see what you can do on your marks, get set, go.